The impact of icing on aviation safety. Aircraft icing remains one of the most critical and persistent challenges in aviation safety. This phenomenon, which occurs when supercooled water droplets freeze upon contact with the aircraft's surfaces, has been responsible for numerous incidents and accidents throughout aviation history. Understanding the mechanisms by which icing compromises flight safety is essential for mitigating its risks and improving overall aviation reliability. Icing typically forms when an aircraft encounters clouds or precipitation containing supercooled liquid water. These droplets are liquid despite being below freezing temperature, and upon contact with the cold surfaces of the aircraft, they freeze almost instantly. The process can result in two primary types of icing, rime ice and clear ice. Rime ice. This type forms when small supercooled droplets freeze rapidly upon impact, resulting in a rough, white, and opaque ice that builds up on the leading edges of wings, tail surfaces, and propeller blades. While less dense, rime ice can still significantly disrupt airflow. Clear ice, formed from larger droplets that freeze more slowly. Clear ice is more solid and transparent, creating a smooth, glass-like surface. This type is especially hazardous because it can spread over a larger area and add considerable weight to the aircraft. The accumulation of ice on an aircraft can adversely affect its performance in several ways. Aerodynamic disruption. Ice alters the smooth flow of air over the wings and control surfaces, degrading the aircraft's lift-to-drag ratio. This leads to a reduction in lift and an increase in drag, making the aircraft harder to control and less efficient. In severe cases, it can cause a stall or loss of control. Weight increase. The additional weight from accumulated ice can degrade the aircraft's performance by increasing the load on the wings and engines. This extra weight can compromise the aircraft's ability to climb or maintain altitude, especially if the ice forms on critical surfaces like wings and tailplanes. Mechanical interference. Ice buildup on control surfaces, such as ailerons, rudders, and elevators, can impede their movement, leading to a loss of maneuverability. Additionally, ice can obstruct engine inlets and sensors, impairing their function and potentially leading to engine failure or erroneous instrument readings. Several notable aviation accidents highlight the severe consequences of in-flight icing. American Eagle Flight 4184, 1994. This flight experienced severe icing conditions that led to the loss of control and a fatal crash, killing all 68 people on board. The investigation revealed that ice had accumulated on the aircraft's wings, disrupting its aerodynamics. Aero Caribbean Flight 883, 2010. This crash was attributed to severe icing that led to an aerodynamic stall and loss of control. The ATR-72 aircraft encountered supercooled large droplets, resulting in significant ice accumulation on the wings and tailplane. Aviation authorities and manufacturers have developed several strategies to mitigate the risks associated with aircraft icing. Anti-icing and de-icing systems. Modern aircraft are equipped with systems that prevent or remove ice accumulation. These include heated surfaces, pneumatic boots, and chemical anti-icing fluids. These systems are critical for maintaining the safety and performance of the aircraft in icing conditions. Weather forecasting and avoidance. Pilots are trained to recognize and avoid icing conditions. Advanced weather forecasting and onboard weather radar systems help pilots identify areas with potential icing hazards and alter their flight paths accordingly. Regulatory standards and guidelines. Aviation authorities, such as the FAA and EASA, have established stringent regulations and guidelines for aircraft certification, operation, and pilot training related to icing. These standards ensure that aircraft and crews are adequately prepared to handle icing encounters. Icing remains a formidable challenge in aviation, posing significant risks to flight safety through aerodynamic disruption, increased weight, and mechanical interference. By understanding the mechanisms of icing and implementing effective mitigation strategies, the aviation industry continues to improve its ability to safely navigate this hazardous phenomenon. Continued research, technological advancements, and adherence to regulatory standards are essential to ensuring the safety and reliability of air travel in the face of this persistent threat.